Welcome to the Explainer. So today we're diving into something that honestly feels like absolute magic. I mean, you type a few random words into a little prompt box and boom, instantly a stunning photorealistic image just appears right on your screen. It's a tech that has completely taken the world by storm. But how often do we actually stop to look under the hood? Well, today we're taking a factory tour of the AI. We're going to literally unbox Latent Diffusion to see exactly how these brilliant systems actually work. Because really, how does a machine turn plain text into a visual masterpiece? To most of us, this whole process is just a complete black box, right? You put words in, you get art out. But beneath that sleek surface, there's actually a fascinating structured assembly line of math and physics. Okay, let's dive right into this.
Section 1. VAE. Shrinking the digital canvas.
To wrap our heads around how this works, we first have to tackle a massive computational hurdle. See, processing raw, high-resolution images, pixel by pixel, that takes a massive supercomputer. So engineers needed a way to shrink the canvas. Enter the Variational Autoencoder, or VAE. It's kind of like packing a massive, overflowing suitcase into a tiny little carry-on bag for a flight. The VAE is basically a neural network component made up of two parts, an encoder and a decoder. The encoder takes a standard 512 by 512 pixel canvas and completely squashes it down into this incredibly dense 64 by 64 mathematical coordinate grid. We actually call this highly compressed, super efficient grid the latent space. It captures the fundamental meaning of the image without dragging along all that heavy, clunky pixel data.
Now, what's genuinely fascinating here is the sheer scale of the compression we're talking about. Let's compare the two. A standard 512 by 512 color image exists in what we call pixel space, and it contains over 780,000 possible values. I mean, that is a massive amount of data for a computer to juggle. But when the VAE compresses that down into latent space, it drops to just about 16,000 values. So the AI does all of its heavy lifting, all its imagining in this lightweight latent space, and only uses the VAE decoder at the very, very end to blow it back up into pixels.
Which brings us to this mind-blowing stat, 48. Because of the VAE, the AI is working on a canvas that is exactly 48 times smaller than the original image. That 48x reduction, that is the revolutionary secret behind the entire AI boom. It's the exact reason why you can run models like Stable Diffusion on a regular everyday laptop with just 8 gigabytes of RAM, instead of needing access to some multi-million-dollar server farm.
Section 2. The diffusion process explained.
All right, so we've successfully shrunk our canvas down to make it super efficient. But how does the AI actually learn to create imagery from scratch? Well, it does this using a concept borrowed straight from physics called diffusion. To sculpt something totally new, the AI first needs raw material. And in generative AI, that raw material is Gaussian noise, basically random static-like visual data. Imagine an old box television tuned to a dead channel, just pure chaotic static. Think of this Gaussian noise as an unshaped block of clay for our AI Sculptor. During its training, this static is incrementally added to a clear image over and over until all the original details are just completely destroyed.
And that brings us to the two big steps of the diffusion training process. Step 1 is forward diffusion. The AI takes a perfectly clear photo, let's say a picture of a dog, and it systematically destroys it. It adds that static noise step by step until the dog is just a blurry, unrecognizable mess of pixels. Step 2 is reverse diffusion. The AI is now tasked with iteratively undoing that exact noise step by step to recreate the dog. By doing this forward and backward dance over billions of images, the AI essentially learns the exact mathematical steps required to reverse the noise. It literally learns how to sculpt a brand new image out of pure static.
Section 3. Clip and U-Net, the sculptors.
But wait, that raises a massive question. If the AI is just staring at a block of random static, how on earth does it know what specific image to sculpt? Like if you type astronaut riding a horse, how does it know to carve that out of the noise? Well, first we have the clip text encoder. You can really think of clip as the guiding blueprint for our sculptor. When you type a prompt, you gotta remember the AI doesn't actually understand English. Instead, a clip tokenizer analyzes every single word you typed and translates it into a massive 768-value mathematical vector. It maps human words to mathematical concepts that the AI can actually understand. It points the AI in the exact direction of what it needs to build.
So, with the blueprint ready, our next component steps in, the U-Net. And the U-Net acts as our chisel. The U-Net noise predictor uses this fascinating mechanism called cross-attention. It looks at the random static on the canvas, then it cross-references your clip text blueprint. It estimates exactly how much noise it needs to scrape away at that specific step to make the static look just a tiny bit more like your prompt. Then, it iteratively subtracts the noise over and over again. Slowly but surely, the static falls away and your final image is brilliantly carved out.
Let's pull this all together and watch the seamless journey of a single text prompt on the Latent Diffusion assembly line. Step 1. Your text is translated into math by the clip encoder. Step 2. The digital canvas is compressed by the VA into that highly efficient latent space. Step 3. Forward diffusion ensures we have a block of raw static to work with. And finally, Step 4. The U-Net carefully chisels away that noise until your masterpiece is fully revealed, which the VA then quickly unpacks back into a high-resolution pixel image.
Section 4. The future of image generation. Honestly, it is a breathtaking architectural achievement. As our sources point out, for the very first time, anyone can download the model and generate their own images. Because the VAE made this entire process 48 times more efficient, it completely democratized generative AI. It took this immense, world-changing power out of the hands of closed corporate systems and dropped it directly onto our personal computers. We are now looking at an open playground for global creativity. Which leaves us with this final provocative thought. As machines master the heavy-lifting mechanics of sculpting pixels from static, what exactly is the new role of human imagination? The technical barriers to creating stunning visual art? They're gone. The AI is the chisel, sure, but you are still the visionary. So how will your creativity evolve now that the only limit is what you can describe? Thank you so much for joining me on this explainer. Keep learning and keep creating.